Hello everyone, how are you? How's everything? I hope everything is going well with you and you're ready for your final assessment, which is going to be tomorrow. So, today I'm just going to take a quick review for you just to tell you what are the most important topics that you need to focus on when you're doing your final review for your assessment. So, of course, as you remember, our main focus for the final assessment is going to be on diodes, on BJTs, and on MOSFETs. Okay, so we'll start with the diodes. So when you're looking at the diode, you have all the lecture notes posted on Moodle for you. So start with lecture note 14. Make sure that you understand the basics of a diode and you understand the operation of an ideal diode. And at the end, I have explained for you how we can make logic gates with diodes. Then you can go to the lecture note 15, in which we have explained the terminal characteristics of the diodes here. What is the breakdown, what is the forward bias, what is the backwards bias, right? So you will see in this lecture note what's going on over here with the diodes. And I would like you to know that how do we model a diode in forward characteristic or realistic diode, because we do have a voltage drop there, right? And of course I would like you to understand what is the breakdown voltage, and at the same time when it comes to the small signal model, I need you to understand how do we model a diode in a small signal. After that, I would like to invite you to check out lecture note 17, in which the Zener diode is explained. Okay, the operation of the Zener diode is explained here for you, and also a circuit model of the Zener diode is explained for you here. So I also need you to make sure that you know how does the Zener diode work, because if you remember, the difference between the Zener diode with the normal diode was that in the normal diode, when we were passing the breakdown voltage, we were actually breaking the diode. It was could not use it again. But the Zener diode, no, we can even use the Zener diode in the backward bias, so not only in the forward bias. The forward bias of the Zener diode is the same, like 0.7. The backward bias of the Zener diode also will give us the VZ that is actually applicable in different circuits, and can make voltage regulators, these things with it. So make sure that you understand the operation of the Zener diode on lecture note 17. Right after that, on lecture note 18, you need to go over the full wave rectifier. Okay, so I have explained for you two different methods to create a full wave rectifier. One was the diode bridge, the bridge rectifier, and the other one was the full wave rectifier with a transformer, step down transformer with two secondaries. Okay, so of course you need to make sure how would each of these full wave rectifiers operate, because this one and this one, these are full wave rectifiers. But if we only use one diode and one diode here and one resistor, we can have a half wave rectifier. But make sure that you know the operation of the full wave rectifier. In lecture note 19, which we're explaining the limiting and clamping circuits, I need you to make sure that you know how the limiting circuit with the diode works, and especially on this slide number 6, please make sure that you understand every single one of these circuits and why do we get this characteristic diagram. Look, these diagrams, they plot the V out in terms of V in. Okay, so please make sure that you know how we're dealing with these clamping circuits. Very important. Of course, at the end here we also explained how we can actually shift a signal up or down using a diode and a capacitor together. So please, this is a very short lecture note, only 9 slides. Please make sure that you understand it very well. Lecture note 19. Then we'll go to the lecture note 20, in which we start to talk about the BJTs. So here we'll start to explain the transistors. So we say that transistors, they have 3 pins. They have collector, they have base, and they have the emitter. Then the semiconductor forming of the transistor is explained over here. The PNP and the NPN, how would it operate? And then different modes of a BJT, the cutoff mode, the active mode, and the saturation mode, which is very important to understand, and how would each of these modes are occurring, and what happens that the transistor goes to any of these modes. Then we talked about the current voltage characteristic, and then we explained about the active mode. Don't forget a couple of things. Don't forget that in the active mode, IC is beta IB, or IB is 1 over beta IC. So beta is one of the characteristics of the BJT that's gonna be given to you. Then if you again follow this lecture note, the properties of the BJT in active mode are summarized in a table here. So the most important part was IC is beta IB, and we should note that IE means the current in the emitter equals to the IC plus IB. We need to know that when we are analyzing a BJT, we are looking to find IC, the current in the collector, and also we are looking to find the VCE, the voltage between the collector and the emitter. And of course, some examples are solved for you. Make sure that you understand these examples very well. And here we also explained how can we use the BJT as a switch. When we use BJT as a switch, we're switching between the cutoff and saturation. In the active mode, we use BJT as an amplifier that I'm going to explain more. But you have to understand what is the edge of the saturation and how would a transistor goes to saturation. Okay, again, I remind you, the transistor at the saturation is good to work as a switch. So when we use a transistor as a switch, as a smart switch, we're switching between the saturation and the cutoff. But when the transistor is in the active mode, and only when it is at the active mode, we can use it as an amplifier. Make sure that you understand all these examples here, and you know how to deal with the transistor, and how to do the DC analysis, and how to find it at the edge of the saturation. You remember, because we said this VCE must be a positive number, otherwise we assume the VCE is in 0.2, which is the VCE in the saturation, and a bit over the 0.2, that we, let's say 0.3, would be the edge of the saturation. Edge of the saturation, we're still in the active mode, but we consider VCE to be 0.3. When we go to the saturation, then the properties of the active mode are not valid anymore. We cannot say IC is beta IB. We're going to have a new beta. We call it beta forced. So you will find the new IC in the saturation, and you divide it by the IB, and you're going to find something called beta forced. So in the saturation mode, we know what is VCE, so we don't need to find VCE. VCE is always 0.2. So using this information, we'll find beta forced. Then we go to the lecture note 23, which is about the BJT and amplifier design. So over here, we have reminded you again that, okay, the saturation and the cutoff are used for this amplifier as a switch, but if you want to use the transistor as a switch, but if you want to use the transistor as an amplifier, we should uh, use it in the active mode, and it's explained for you that why actually we can use the transistor as an amplifier in the active mode. You see that a small change in the VPE can create a big change in the VCEs. That's why it can be working as an amplifier. So how to do it? To actually, when we want to analyze an amplifier circuit including a transistor in active mode, we need to do a DC analysis first. After conducting the DC analysis, we're going to find a parameter called we find IC. Then we will find the parameter called GM with this formula, IC over VT. That VT is a constant, like 25 millivolts all the time. And then we'll find another parameter called R pi, which is basically beta over GM. Since we are in the active mode, look, you have to be in the active mode to be able to do the AC analysis. Then you will find R pi, which is beta over GM. Then you will model your transistor with this model. We call it the pi model, in which the whole transistor is modeled with this shape with the resistor R pi and GMVPE. So here's your base, here's your emitter, here's your collector. And then you will add the rest of the components that were in the circuit. You also have the option to use another model called T model, but I recommend you to stick to the pi model, which is very easy to deal with. And I have summarized for you at the end how to analyze a transistor circuit in AC. You just eliminate all the small signal sources first, all the AC sources first, and just keep the DC. So do the DC analysis. After you did the DC analysis, you will find IC. When you found IC, using the IC, you will find GM. Then using GM, you will find R pi. Then you will eliminate all DC sources, and also you will replace the transistor, your BJT, with the pi model that I told you. Then you analyze this new circuit model, which is a very simple thing to do. After that, we go to the lecture note 24, which we start to explain the MOSFET, which was metal oxide semiconductor field effect transistor. That's MOSFET. So here we have explained to you the semiconductor nature of this transistor and what is the basic operation of this type of the transistor. Then I have started to tell you the features of this transistor. How do we actually show this transistor in a circuit? We have p-type and n-type. The p-type is like analogous to the PNP transistor over there. The n-type is like NPN transistor. So the p-type, we show it this way. We have 3 pins here. We have gate, drain, and the source. And instead of base, collector, and the emitter, we have gate, drain, and source. And as you remember over there, like this arrow over there was following the emitter in the BJT. Here in MOSFET, this arrow follows the source all the time. Over there, you remember that the current in the drain, in BJT, the current in the collector was beta times more than the current in the base. Here in MOSFET, it's even easier. Here we have 0 current in the gate. So the current in the drain and the source are always equal. Simple as that. And the current in the gate is always 0. So like BJT, that we used to have 3 different modes. Over there you used to have cutoff, active, and saturation. Here you have cutoff, triode, and saturation. Like triode is like active mode. So to be able to figure out in which region we are, we need to check the conditions. First, we check VGS. What is VGS? The voltage between the gate and the source. If this voltage was smaller than a certain voltage, we call it threshold, VT. For the NMOS, we call it VTN. For PMOS, we call it VTP, the voltage of threshold for NMOS, this VTN, that's how we did. So if VGS was this, and this is a given, this is one of the characteristics of any transistor, that it has to be given in any problem that you're solving. So if your VGS was smaller than VTN, you're in the cutoff. If your VGS was bigger than the VTN, so you're not in cutoff, so you're either in triode or saturation. So you should check VDS now. It means the voltage between the drain and the source. If this VDS was smaller than VGS minus VTN, you're in triode. If it was bigger than VGS minus VTN, you're in saturation. And for each of them, I have given you the formula to find the ID, which is the current in the drain or the source, because the current in the drain and the source are totally equal, because we have zero current at the gate. It's very important. For the PMOS, it's the other way around. For the PMOS, if VGS was greater than V of the threshold, we are in the cutoff. If it was smaller, then we'll check. If VDS was greater than VGS minus VTP, we're in triode. If VDS was smaller than VGS minus VTP, we're in saturation. So keep this in mind, and when you're having an example, make sure that to see whether we are in PMOS or NMOS. What is this one? Right, it's a PMOS, but this one is an NMOS. Okay, in the NMOS, this arrow is down. In the PMOS, this arrow is up. So in the NMOS, drain is up, source is down. In the PMOS, source is up, drain is down. Okay, keep this in mind, and make sure that in lecture note 24 you know this slide number at the end, the summary slide, which I have explained how to check for the region and how to find the current for each region. And last but definitely not the least is the amplifier application of the MOSFETs. So here you have to remember one thing here, that unlike BJT, MOSFET can work as an amplifier only in the saturation mode, unlike BJT, because BJT was working as an amplifier when we were in the active mode. But in MOSFET, no, you can work as an amplifier when you are in the saturation mode. Here it's explained, different regions are explained, and you can see why only in the saturation mode the MOSFET can operate as an amplifier. And here also the gain of MOSFET is explained and everything, but one thing is important here. After you did the DC analysis here and you found the ID, the current in the drain, you find the GM. So how do you find GM? GM is simple. GM is found simply using this formula, K prime of N W over L VGS minus VT. W is the width, L is the length. So these also usually are given to you. Or no, in some some problems, either W or L can be the unknown, but ID must be given to you. You can find it. So technically you will not have more equations than the unknowns when you do the analysis. One of these things, either W, L or ID, could be the unknown here, but the rest must be given. So in this one, after you found the GM, you will model your MOSFET with this pi model, which is much easier than BJT, because there is no resistor here. In BJT you used to have something called R pi here, right? But since you have the luxury of not drawing any current in the gate when it comes to MOSFET, you simply do not need to have any resistor here As simple as that. And this is how you model your MOSFET. And if I want to summarize the steps, so in order to do the AC analysis, first you do the DC analysis. How to do the DC analysis? You will remove all the sources, all the AC sources, right? You just keep the DC. And when you just keep the DC, of course, all the capacitors are going to be considered open circuit. And then you will do the DC analysis. Then you will find ID, and you will make sure that your MOSFET is in the saturation mode. Then when you want to do the AC analysis, you remove all the DC sources. So you ground them. And then the capacitors here are going to work as a short circuit. And then you replace your MOSFET with this model. Here also you have two models. You have the pi and you have the T, but I recommend you to stick to the pi model. And then you simply analyze the resulting circuit. Thank you very, very much. I hope everything is going to be fine with you. Everything is gonna be straightforward. Just be confident, study well, take a deep breath. You're gonna be done very soon, and I'm sure you're gonna do very well. Take care, have fun, and see you soon. If you had any questions, just send me an email or ask me tomorrow in class. Take care, bye bye, thank you.